For section 3.2, we'll be introducing the angular measure called the radian. It is a unit of measure which tells us how much rotation there is, which is similar to what a degree does. The numerical value of the radian is not equal to the numerical value of the degree. In fact, the radian is constructed to associate the measure of a rotation to the distance that would have been traveled along the arc of a circle, called an arc length. The definition of the radian can be recalled, for example, if we can imagine, this is the way that I would suggest recalling how a radian is defined. If we take the unit circle, recall that the unit circle is a circle centered at 0, 0, that has a radius that is equal to 1 unit. For example, if the radius is 1 foot, 1 mile, 1 astronomical unit, 1 meter, okay, for example, that would be the unit circle. Okay, so r is equal to 1 unit in the unit circle. The distance that an object would have traveled along a circular path, let's say we'll put an angle in standard position, like so. So if theta is right here, okay, and if theta is positive, then we're moving in the counterclockwise direction. Then the value of theta in radians, that is the numerical value of theta, which is being measured in radians, is going to exactly equal the distance that was traveled along this arc right here. We're going to call this distance here the variable t. Okay, that's the distance traveled along the arc of the unit circle, okay, and that's called an arc length. That is a distance. The distance along the arc is going to have the same units as the radius. So if the radius of the circle was measured in, let's say, in feet, then the distance traveled along this circular path is also in feet. This is a curved distance, not a straight line. This is not a triangle here. This is a circular sector. Okay, so this is a curved arc right here, like a slice of pie or a slice from a pizza, circular pizza, right? It's kind of rounded here. So if t is the distance traveled along this path, and that's associated with the angle that is in the center of the circle, okay, then whatever the numerical value of the angle is, which when it's measured in radians, will exactly be equal to the distance that is traveled. Okay. So for example, if we are saying we are in the unit circle, where let's say that r is equal to 1 foot, that is the radius of the circle is 1 foot, okay, then an angle of, let's say, 2 radians, okay, can immediately be associated with a distance traveled along the circle of 2 feet. So if theta is equal to 2 radians in rotation, we say that there's also a distance of 2 feet. The radian measure is constructed so that these numerical values will always be the same. The amount of rotation will always be exactly equivalent to the distance that was traveled along the circle as associated to that rotation, if we are in radians, not in degrees. So 2 radians is not the same as 2 degrees. Okay? And this is only going to be exactly true when we are in the unit circle. In fact, if we go outside of the unit circle into a circle where the radius is not 1, then we're going to multiply the radian measure by the radius in order to find the arc length. And we'll see that formulaically showing up in this section and the next. This is a way I suggest to remember what the radian is. It is the angle within the unit circle such that the angle, the numerical value of the angle, is always equal to the distance along this circular path right here. Now, because the numerical value of the radian Okay, the number that's being used for the radian can be interpreted as either the amount of rotation or the amount of distance, the same number, right? Then oftentimes, okay, the radian measure of an angle can be a unitless measure. Okay? So radian measure is often going to be unitless. That is written without any units. So when we say that an angle is equal to a number, but don't indicate what unit that angle is being measured in, then we assume that it was measured in radians. So when we read an expression like the sine of 30, we assume that the 30 means 30 radians. We do not assume it means degrees. We assume automatically it must mean radians because we weren't told whether it was radians or degrees. If we had intended to write the sine of 30 degrees, we must write the degree symbol. So if an angle is meant to be in degrees, you will be told it is in degrees. And if you intend for your angle to be interpreted in degrees, if you submit work to me or to someone else, if you're intending to use degrees for your angle, you need to write the degree symbol as well. Because if you don't write the degree symbol, then the correct interpretation would be that you meant to say it was in radians. Okay? Now the reason why the radian measure is often without units, can be written as a unitless measure, just a number with no units, is because that number might be interpreted correctly as either a rotation or as a distance, where the distance would be in the units of whatever the radius was for the unit circle. Okay. So we want to define the radian in this way to allow us to talk about circular distances, arc lengths, as they associate to rotations within the circle. And this allows us to further define trigonometry, okay, and in a periodic sense along circular orbits or circular motions, repeated behavior as it moves along a circle. Okay. Now you have the conversion here for between radians and degrees. Why is that the conversion factor? That pi radians equals 180 degrees. We'll take a look at why that is. And if theta is measured in radians, then theta equals s over r. This is already going to be true anytime we're in the unit circle. Remember that the unit circle, it's called the unit circle because the radius is 1 unit. So if you made r equal to 1 right here, then this equation says that theta equals s, where s is the arc length of the circle. Okay? T is the variable that's going to be used for the arc length of the unit circle. S is going to be the variable that we use for the arc length of any circle in general. We'll need to evaluate trigonometric functions using radians. There are 2 ways to do this. One is you can convert the radian into degrees. If you're more comfortable using degrees, at this point we've exclusively been using degrees. But I want to make note that from this moment on, throughout this course and in future courses, trigonometry is built off of the radian unit of measure for the angle, more exclusively than the degree. So you'll be using radians more frequently than degrees from now on. But if you're comfortable with degrees, if you're more comfortable with degrees, one option you have for evaluating functions with radians is you can start by converting radians into degrees. For every pi radians, you get 180 degrees. So we can get these unit ratios, which is going to allow us to convert to degrees if we want to. The other option is to start memorizing and focusing on the evaluations of trigonometric functions using radians as the input. Okay. Here are the most common angular measures that we have listed in degrees on the right and listed in radians on the left. For instance, 0 degrees, well, that's 0 radians. 30 degrees is pi over 6 radians. 45 degrees is pi over 4 radians. Notice again on the left-hand side, I'm not writing the units after these numbers. Like pi over 4 just says pi over 4. But on the right, I am writing the units, their unit of degrees. Okay, this allows for us to interpret the numbers on the left here these radian numerical values, we can also interpret them as the distances that were traveled along the circular path if we had a unit circle. Okay. And for reference angle, we talked about reference angle recently. Well, we dealt with reference angle, for example, when theta was between 0 and 360 degrees. Then we looked at what if theta was negative and what if theta was more than 360 degrees. Okay. As a basis for the same discussion using radians, we're going to say, well, if theta is anywhere between 0 and 2 pi, and we'll talk about in a moment why that's the correct interval to start with. If theta is anywhere from 0 to 2 pi, that implies radians. Then the conversions are going to be the same as they were with degrees. It's just instead of 180 degrees, we're using pi, because pi radians is 180 degrees. And instead of 360 degrees, we're using 2 pi. Okay, now why the interval 0 to 2 pi? Why is that analogous to the interval from 0 to 360 degrees? Okay, which is, right, I'll make a note of that right here, right? This is the same as saying that we are going from 0 degrees to 360 degrees, okay, but using radians instead of degrees. So 360 degrees is associated with 2 pi. Why is that? We'll start with the actual definition of the radian. Okay, I said over here how to remember what a radian is. That's the way I remember what a radian is. Okay, for instance, if we have 1 radian of rotation here, it's associated with a distance of 1 unit along this circle. Okay, so the radian is defined so that the ratio of the arc length to the radius is always equal to the radian. Okay, so S is equal to the arc length, okay, in any circle. Okay. Recall I used T to represent the arc length specifically in the unit circle. Remember, unit circle means the radius is equal to 1. So we define the radian specifically in this way. Okay? And the reason why is by this equation we are able to directly associate rotation to distance, rotation to arc length. They are being related to each other by this equation. And this equation is only true if the measure of the angle is in radians. This is not a true equation if theta is measured in degrees, only in radians, because that's the way the radian is defined, to be used in exactly that way, to tell us about distance when we know angle. Okay. Now, why is it that we're talking about theta being from 0 to 2 pi as compared to degrees from 0 to 360? Well, consider the case where we were talking about traveling along a circular path the entire distance around the circle, that is the circumference of a circle. Okay, if we went around an entire circle, okay, and if we were in, let's say, the unit circle even, right? So again, in the unit circle, okay, let's say if T is the distance around the entire circle, then that means that T is equal to 2 pi. Because the circumference of a circle, right? The circumference of a circle is 2 pi times r. But if it's the unit circle, then r is equal to 1. So the circumference is equal to 2 pi times 1. So I'm saying if we travel around the entire path around a circle, right, then the circumference would be 2 pi. That's the distance we traveled around the circle, where the units of measurement for the 2 pi would be the same units that were used for the radius. So if the radius was equal to 1 foot, then we have traveled 2 pi feet, that's about 6.28 feet in distance to move around the circle in one rotation. Okay. Well, what theta would that specifically be associated with in standard position? Okay. The theta would be the amount of rotation, okay, would be this amount of rotation right here. So we have r is equal to 1, we have t is equal to 2 pi. That's the arc length in the unit circle. We could use s to describe that arc length as well in general, but because we're in the unit circle, I'm using the letter t, and we'll continue to do that as we move ahead into future sections. And then by this formula right here, then, what is theta? Well, theta is equal to the distance we traveled, which is 2 pi, divided by the radius, which is 1, because it's the unit circle. So theta is equal to 2 pi. All right, so we say, okay, so if theta is equal to 0, we have no rotation at all. All right, if we don't rotate at all, then the distance we traveled is 0. If you don't rotate, then the object doesn't move. But if you rotate through a complete rotation, a complete revolution, which would be equivalent to 360 degrees, if we were in degrees, that has to be associated with 2 pi radians. Because in the unit circle, the distance around the circle is always exactly 2 pi of the units of measurement for the distance in the circle. So we get that theta, right? If theta is equal to 360 degrees, that is equivalent to 2 pi radians. I don't have to write radians here, right? If I don't write the word radians, we assume the 2 pi is measured in radians. But I'm writing it now for emphasis. 360 degrees of rotation is always equivalent to 2 pi radians. And so take that equation right there. If 360 degrees is equal to 2 pi radians, then notice if we divide by 2 on both sides of this equation, then that means that 180 degrees is exactly equal to pi radians. And therefore we can create unit ratios like pi over 180 degrees. That's pi radians over 180 degrees. And the reciprocal of that, 180 degrees over pi radians. These are the unit ratios we can use if we want to convert from degrees to radians or from radians to degrees. Okay, so now included in the lecture notes, I typed out solutions, worked through for a variety of examples. Let's take a look at some of those examples right now. Okay, this first example, convert 30 degrees to radians. So it is a unit conversion that we're doing. And we've done unit conversions before in this class. We just need a unit ratio. So let's try that one out. Or we could do a similar one. All right, should we do a similar one? How about convert 60 degrees to radians? Okay, well, we're starting with 60 degrees. We multiply by a unit ratio. Okay, 60 degrees or 60 degrees over 1 if you want. Okay, the unit ratio that we want should have the units of degrees in the denominator, so we can cancel degrees with degrees, and then should have the units of radians in the numerator. That way we would convert from degrees to radians. Recall the conversion is pi radians is equal to 180 degrees. So we can put pi on top of this fraction and 180 on the bottom of this fraction. 60 degrees times pi radians over 180 degrees then. Okay, so we get to cancel degrees with degrees. We'll be left with radians. We multiply straight across, you get 60 pi over 180, and that's the amount of radians. And then we can reduce, and this reduces to pi over 3 radians. So 60 degrees is the same as pi over 3 radians. So to give you an idea and a notion for what we can do with this radian measure, let's say that we are in the unit circle. If you're in a circle with a radius, let's say, of 1 meter, a circle of a radius 1 meter. Okay. What arc length, okay, I'm going to use this word, subtends a rotation of pi over 3. Okay, so subtends, okay, by the geometric definition. So it's going to be the distance along the arc over that angle. A rotation of pi over 3. Note, pi over 3, I have written as a unitless measure. I've declared it to be a rotation. And if a rotation is given as a numerical value without any units, then we assume that it is in radians. So if I said a rotation of 20, then I assume I meant 20 radians. We do not assume 20 degrees. Okay, so geometrically representing this, let's see, I get a circle. Okay, let's pretend that this is a circle here, first of all. Okay, I'm not very good at drawing circles on this thing. Okay, and the radius of this circle, r, okay, is equal to 1 meter. Okay, so if r is equal to 1 meter, if we were to rotate through, I should put r underneath this. Here we go, right down here. If we were to rotate through an angle of pi over 3, which in degrees that would be 60 degrees. Okay, so let's say approximately 60 degrees. So let's say this is theta right here. Okay, so we have theta is equal to pi over 3, which is equivalent to 60 degrees. So it should look like that amount of rotation right there. Okay, then the distance that would have been traveled along this arc by an object. Okay, you can imagine. Let's say we're standing at a point with maybe a rock tied to the end of a string, and we're sort of swinging the string or something like that, right? So it's extended outward along the length of the string, and it's moving in a circular path. If we were to rotate it through 60 degrees of rotation, then what distance did the object actually travel along that path? And the distance it would have traveled in the unit circle is, we can use the variable t. If it was at the unit circle, we should use the variable s. Okay. The distance it would have traveled would have to be pi over 3. And in units of distance, it would be the units of meters. Okay. Units of meters. Now, what is pi over 3 then as a real number? So if we write it as a decimal, so we'll do an approximation here. So pi over 3 is approximately 1.05. So it's saying that this object traveled about 1.05 meters in distance along this path as being associated to an angle, a rotation of approximately 1.05 radians of rotation. Right? So the numerical amount, the number that represents how much rotation there is the exact same number as the distance the object actually traveled. It's the units that are changing here. Right? If it's radians, then it's angle. And if it's a distance unit, well, then it's an arc length. But the numerical value, the number we're using, is exactly the same number as long as we're in the unit circle. If we're not in the unit circle, then we can use the formula that associates the angular measure to the arc length. So let's take a look at that. Okay. In a circle, with a radius of, let's say, 3 meters. Same question then. What arc length subtends a rotation of pi over 3? So it's the same question, I'm just taking the radius to be 3 meters now. And if the radius is not 1, then we are no longer in the unit circle. Alright, so the picture would be, really, it would look like the same picture, alright, only labeled with a different radius. So here's r, okay, so now we have r is equal to 3 meters. Alright, we are still rotating through an angle of 60 degrees, alright, that is pi over 3, which is 60 degrees, which is approximately 1.05 radians of rotation. Okay. But what is the distance now that we have traveled? The distance from the initial point along the circular curve to the terminal point, okay, going to call that S. Okay, and by definition of the radian unit, theta, when in radians, is equal to S divided by R. Okay, only true if theta is in radians. Okay, so this is only true if theta is in radians. If theta was in degrees, you would want to convert it into radians before going to a formula like this. Okay. So anytime you want to, for instance, find an arc length, okay, for example, if you're using an angle that's measured in degrees, you should think first you need to convert to radians so that then you can access the formulas that tell you about distances along a circle. Okay, so theta equals S over R, and we're asked what is the arc length subtended. That subtends a rotation of pi over 3. And that arc length would be S. Okay. This formula tells us that if we multiply theta times R, we will get S. And S is the arc length. That's what we want. So we use the value for theta in radians, okay, the value for theta in radians, which is pi over 3, and we multiply by the radius, which is 3 meters. And that gives us a distance S. What distance does that give us? Pi over 3 times 3 is pi, and the units of measurement here are meters. So pi meters is equal to the arc length then. Okay? That is the distance the object would have traveled here, in this example, is approximately 3.14 meters of distance. When given that pi over 3 was the amount of rotation, right, which is in radians, we multiplied that by the radius. That gives us distance units. Okay? And we get pi units of distance was traveled by the object along the curve. Okay, so we have so I've given you a couple examples here, converting degrees into radians. Work those examples through using unit ratios. Okay. What if we wanted to convert from radians to degrees, though? However, you may find, personally, you may find that you think it's easier to work with degrees for your angles. And if that's the case, maybe you just want to convert your radian measured angles into degrees. How do you do that? Well, we can do this with any value of radian measures, but I'm going to specifically focus on ones that are more commonly seen. But let's say we take, so a lot of times using the pi in it. So you see 7 pi over 6 being converted into degrees by multiplying by the unit ratio, 180 degrees over pi, converting 17 pi over 18, which must be a radian measure for the angle because it doesn't say the units, right? So converting that number to degrees, multiplied by 180 degrees over pi. Okay. So I'll do one more example here. How many degrees would be equivalent to 1 radian? Okay, and let's round to, let's round to the nearest whole number. Round to the nearest whole number in this case. How many degrees would be equivalent to just 1 radian? That is, we want to convert 1 radian into degrees. So we write 1. Okay, I'll even write rad there so we explicitly know that we mean radians here. We multiply by the unit ratio. The unit ratio should have radians in the denominator so we can cancel radians with radians, and degrees in the numerator to allow us to convert to degrees. And the conversion is, again, that for every 180 degrees, we would go through pi radians of rotation. So we can cancel radians with radians. And we get 180 divided by pi. That's the amount of degrees. That is equivalent to 1 radian. Now, how much is that approximately? Rounded to the nearest whole number. So 180 divided by pi Okay, first off, comes out to 57.29578. I'll stop there, and then degrees. Round that to the nearest whole number. 1 radian is approximately the same amount of rotation as 57 degrees, or 57.3 degrees if we were going to 1 decimal place. Okay. Every 1 radian is approximately 57 degrees of rotation. Okay, so let's take another look at a circle. Okay, here's a circle, sort of, right? Okay, so in standard position, if we traveled through 1 radian, that would be about 57 degrees. So that's about maybe this much in rotation, maybe a little more than that, maybe like this. It's about 60 degrees, not quite. Okay, so this is 1 radian. Rotation is right there. What would 2 radians be? Right, 2 radians would be approximately, well, 57.3 times 2, right, would be like 114.6. Okay, so 114.6 degrees. So about 115 degrees. So more than 90 degrees. Right? That's more than 90 degrees. Okay, but but less than 180 degrees, right? So if this is an additional 1 radian, of rotation right here, then we now have a total of 2 radians of rotation in standard position. Okay, so 2 radians in green. What about 3 radians? Well, 3 radians would be this plus another 57.3 approximately. Right? Notice that's almost 180. Okay, it's almost 180 degrees. What's that about? Let's see, 160, 170. It's going to be like 171.9 degrees. Okay, so it's a little bit less than 180 by the time we get to 3 radians. So if this is, right, so this is not the scale, right? I mean, these should look like they're about the same size. Let's see, if this is 180 degrees right here, all right, maybe something like so. Okay, so that's another 1 radian of rotation right here. Okay, and then we'll take purple. So 3 radians, okay, is this amount of rotation. And that's about 172 degrees. It's a little bit less than 180 degrees. Okay, and then recall, of course, our conversion factor. Pi radians, which is approximately 3.14 radians, a little more than 3 radians, right? That would be equivalent to 180 degrees of rotation. So just a little bit more than 3 radians and we'd be halfway through the circle. So every 1 radian will be approximately 57 degrees of rotation. Reference angles for radians. Okay, simply put, if pi is replaced by 180 degrees, then these are the same statements that we saw when using degrees. So we can use that to do evaluations of trigonometric functions. Let's take a look at that right now. Okay, so I show you here how to find reference angles. For example, if you can either convert the reference angle into degrees and then convert back from degrees into radians. That's one way to do it. Okay, or it would be helpful to associate the quadrantal angles to radian measures of the quadrantal angles. Recall that quadrantal angles are angles that would terminate on an axis. Let's take a look at those. The quadrantal angles, okay, those are the ones that terminate on an axis, either the x-axis or the y-axis, and they are not in any given quadrant, because the axes are considered to be between quadrants. Okay? Quadrantal angles using radians, okay? The primary ones at least. All right, so we had this was 0 degrees, to be pointing in the positive x-axis direction, that is equivalent to 0 radians. Okay. Then if we rotate in standard position in the positive direction, counterclockwise, if we were to rotate to the positive y-axis, we would be at 90 degrees. Right. 90 degrees is equivalent to pi over 2 radians. Right? Remember the conversion, 90 degrees times pi rad over 180 degrees. So we can cancel, right, so this way we can cancel degrees with degrees, the units. You get 90 pi over 180. 90 goes into 180 2 times, so this becomes pi over 2 radians. 90 degrees is pi over 2 radians. And of course, 180 degrees, if we were to rotate towards the negative x-axis, that is, of course, equivalent to pi radians. Okay. 270 degrees, that would be along the negative y-axis, 270 degrees. Convert that into radians, pi radians over 180 degrees. Right, that's 270 over 180 times pi. In radians, reduce this, they both divide by 90. So this would be 3 pi over 2 radians. 270 degrees is equivalent to 3 pi over 2 radians. And then if we were to go through a full rotation in the counterclockwise direction, we would get back to the positive x-axis again after 360 degrees. That's 2 times 180, so that's 2 pi radians. Okay, and then it would continue beyond that if we would go outside of the range from 0 to 360. Okay, so quadrantal angles using radians, okay, in an initial rotation from 0 degrees to 360 degrees, okay, because we can certainly extend this beyond that. We can go to, we can go through a full rotation and then some. Right? We would be at, 450 degrees. We can go through a full rotation and another half of a rotation, for example, and be at 540 degrees. And all of those degree measures can be converted to radians. We can also rotate in the other direction. We can rotate in the negative direction. And we can say that this would be negative 2 pi radians because it was negative 360 degrees if we were to rotate in that direction. Okay, we can always convert our degree measures of angle into radians. Okay, so let's say that we want to find a reference angle. Okay, let's find the reference angle. Okay, for let's say theta is equal to 7 pi over 9, for example. Okay, so 7 pi over 9, first of all, is 7 pi over 9 is between 0 and 2 pi. How do I know? Well, we can see that it's larger than 0 because it's a positive number. How do we know that it's less than 2 pi? Because 2 pi, if written with a common denominator as 7 pi over 9, we can multiply by 9 over 9. 2 pi is the same as 18 pi over 9. And we could agree that 7 is less than 18. So yes, 7 pi over 9 is less than 18 pi over 9. Okay, so this means that we are within the initial rotation from 0 to 360 degrees. That is from 0 to 2 pi radians. Okay. Now, which quadrant is this in? Which quadrant contains 7 pi over 9? Right? We have 0 here, we have pi over 2 here, we have pi, and we have 3 pi over 2, and then we're going to get 2 pi when we get back to here again. Right? Notice, how does 7 pi over 9 compare to, let's say, pi over 2? Okay. Well, let's see. If pi over 2 and 7 pi over 9 had a common denominator, pi over 2, let's say I multiplied that by 9 over 9, that would be 9 pi over 18. Okay, convert 7 pi over 9 into a number that has a denominator of 18 as well. 7 pi over 9 times 2 over 2 is 14 pi over 18. So which one is larger? Pi over 2 is equivalent to 9 pi over 18. 7 pi over 9 is equivalent to 14 pi over 18. Right? So we see that 7 pi over 9 is greater than pi over 2, because 14 pi over 18 is greater than 9 pi over 18. Okay? And furthermore, 7 pi over 9 is going to be less than pi, because pi is equivalent to 9 pi over 9. So we can agree that 7 pi over 9 is less than 9 pi over 9, okay? And it's more than 9 pi over 18. So 7 pi over 9 must be between pi over 2 and pi. That means it must be within quadrant 2. Okay, so here's our theta. Okay, we are in quadrant 2. Okay, so what's the reference number? When you're in quadrant 2, the reference is found by the amount of rotation left to get back to the x-axis. That's the amount right there, that amount of rotation. Okay, so how much remaining rotation is that in green there? Okay, that is the reference number in green in quadrant 2, okay, is equivalent to pi, which is equivalent to 180 degrees, minus theta. Okay. So that is pi minus 7 pi over 9, which is equal to 9 pi over 9 minus 7 pi over 9. Right, jumping ahead there. Okay, 7 pi over 9, which is equal to 2 pi over 9. Okay, so the reference number, or reference angle, is equal to 2 pi over 9. Okay, so establishing which quadrant it's in, okay, by knowing which quadrantal angles it is between. If this were a rotation that was more than 2 pi, we should subtract instances of 2 pi until we get a coterminal angle that is between 0 and 2 pi. Similarly, if we're given a negative angle, we could add instances of 2 pi, that is adding full periods, until we get an angle that is between 0 and 2 pi, just like we did with degrees. Speaking of just like we did with degrees, the other option we have here that you might prefer here at the start would be to convert this from the start into a degree measure, and then just proceed with it as if it was degrees. Okay? So the other option that we had, or we can simply start by converting, right? We can convert 7 pi over 9 to degrees, okay? And then proceed. And then to proceed with finding theta hat. But note, okay, we're going to have to convert theta hat back to radians if we choose to do it that way, because the answer is expected here to be in radians. Even if you do the problem using degrees, okay, the given question, we started with an angle in radians, we're going to want to get back an angle in radians as well. Okay, so we've already seen how to convert into degrees. A real quick conversion, right? 7 pi over 9 is a measure in radians. Well, if we multiply by 180 degrees over pi radians, we would get it converted. Okay, right? Because this would allow us to cancel radians with radians. Right. So we have 7 pi over 9 times 180 over pi. Got more cancellations here. We can cancel pi with pi. We can also reduce dividing 180 divided by 9. 180 divided by 9 is 20. And then we can multiply straight across. We'll get 7 times 20, which is 140 degrees. Okay? And We know that 140 degrees is between 90 degrees and 180 degrees. Furthermore, we know that the reference would be 40 degrees. That's 180 degrees minus 140 degrees. Then convert 40 degrees back into radians. You'll get 2 pi over 9. Okay. So it's helpful to get some practice using the angles pi over 2 pi, 3 pi over 2, and 2 pi. Start getting used to radians being the primary angles that we're going to be using in trigonometry for the future. And again, so that we can talk about more applications using trigonometry when associated with distance, and when using where the input to the trigonometric functions does not have to be an angle anymore. The input can actually be a distance. And that's primarily how we use trigonometry in practice. Okay, so we got reference angles. How about evaluating expressions by using the reference angles? Okay, evaluate, for instance, sine of 7 pi over 6. Okay, one option is you can convert 7 pi over 6, or the argument, if you will. You can convert it into degrees if that's what you want to do, and then evaluate it the way that we already have with degrees. To get used to the radian measure, though, we should do the same idea as what we did with degrees, but using radians instead. That is, we want to note what quadrant the angle is in and what the reference number or the reference angle. Okay. Let's say evaluate. How about the cosine of 11 pi over 6? Cosine of 11 pi over 6. Okay. So one option, we can convert to degrees, then proceed as we had previously in the course, okay? Or just stick with using radians. In either case, the two ingredients that we need to have the quadrant, okay, the quadrant for the argument. In this case, the argument is 11 pi over 6, and we need the reference for the argument as well. Whether we use degrees or radians, we're going to want those two things. Okay, so let's find that out for 11 pi over 6. Okay, if theta is equal to 11 pi over 6, okay, this is what, pi over 2, pi, 3 pi over 2, 0, and also 2 pi. Let's see if we can get a common denominator in all these cases. Pi over 2 with a denominator of 6 would be 3 pi over 6. Pi with a denominator of 6 would be 6 pi over 6, right? That's equivalent to pi. 3 pi over 2 is the same as, let's see, multiplied by 3, so 9 pi over 6. And 2 pi is equivalent to 12 pi over 6. So 11 pi over 6 is going to be between 9 pi over 6 and 12 pi over 6. Okay, so if we wanted to sketch in standard position the angle with rotation 11 pi over 6, it should rotate through into quadrant 4. Okay, so 11 pi over 6 is found in quadrant 4. And the reference, right, so again, this is quadrant 4, right? And the reference is the amount of rotation remaining to get back to the x-axis. How much rotation is that? Okay, that's theta hat. So theta hat is found in quadrant 4. Theta hat would be found by subtracting from 2 pi. So 2 pi minus 11 pi over 6, which is 12 pi over 6 minus 11 pi over 6, and that equals pi over 6. So we have the quadrant. It's quadrant 4. That'll tell us whether this is going to be plus or minus. All right. And we have the reference, which is pi over 6. So now we have the cosine of 11 pi over 6 is equal to, we have to figure out is either plus or minus the cosine of pi over 6. All right, so recall that the cosine of theta is equal to plus or minus the cosine of theta hat. All right, where this is determined by quadrant. Right, and theta hat is the reference. So we need the cosine of pi over 6, and we need to know if it's positive or negative. We're in quadrant 4. In quadrant 4, the cosine is positive, so this is going to be positive. And the cosine of pi over 6, if it helps, pi over 6, recall, pi over 6 is the same as 30 degrees. So you want the cosine of 30 degrees. And the cosine of 30 degrees is root 3 over 2. So the cosine of pi over 6 is also going to be root 3 over 2. Right? So recall that the cosine of 30 degrees is root 3 over 2. So the cosine of pi over 6 is root 3 over 2 as well. Okay. So we use the reference number in order to find out the numerical value, the magnitude of this, the cosine of pi over 6, okay, which is the same as the cosine of 11 pi over 6. Okay. And then we have to know the sign. That's the plus or minus SIGN, the sign, okay, which is determined by the quadrant. That's why we need to know the quadrant and the reference. If we had done the conversion to degrees, then convert to degrees. 11 pi over 6, you could multiply that by the unit ratio 180 degrees over pi radians. Okay, you only get the number of degrees. It's going to turn out that 11 pi over 6 is 330 degrees. Okay, 11 pi over 6 is equivalent to 330 degrees. You can find that by using the unit ratio to do the conversion. And then you could find out what's the cosine of 330 degrees, which requires that you know the quadrant, which is quadrant 4, and the reference is 30 degrees. Okay, so that takes care of the variety of types of exercises you'll see in this section, introducing the radian measure. You can do conversions from radians to degrees. You should also be able to convert from degrees to radians. And there are ways in which you can work through exercises by using either radians or degrees. In a lot of cases, it is your choice which one you do, and whatever your preference is. In general, there are going to be fewer steps required if you stick with radians. Okay? But you might find that you have an easier time working with degrees. Be mindful of when you need to convert back to radians, though. If you convert into degrees, the problem's instructions might require that you convert back to radians later in order to give an answer. And note that we're always going to give preference to radians, particularly when we're going to be dealing with distances along a circular path. That is called the arc length. So any question involving a distance along the edge of what would be the shape of a circle, expect the radian measure to be primarily used for the rotation. If you're given an angle in a circle, but the angle is in degrees, and then you're asked a question about the distance traveled along that circle, then you should convert from degrees to radians, because the radians can be associated with the distance along the circular path, okay, by the definition of the radian. Theta is equal to S divided by R, or similarly that S is equal to R times theta, the arc length formula. Okay, so try out some of the exercises from the homework and let me know if you have any questions or run into any problems or have any concerns. Okay, take care.